Good afternoon and welcome back. This is CS240 and we're going to get started exactly where we left off. So we have been talking all semester long about the foundations of a computer system. And we're getting really close to the point that we're going to be building applications that span multiple systems. So today we are releasing your very final CMP. Because C is a fantastic programming language that allows you to work deeply within your own system very easily. C is a terrible programming language for working between multiple systems. There's just a lot of stuff that gets abstracted away as soon as you are building, as soon as you don't have to be on one system, you just want to be able to send network packets and receive data over a network form of IPC very quickly and efficiently. And Python lets you do that. So today we're going to wrap up networking at a byte level. And we're going to start talking about HTTP packets and protocols and how do we send data between multiple systems and how do we organize that data between all of the different systems. So where we left off has been this idea that we want to do networking. And the big thing with networking is just a stream of zeros and ones. The reason we started with hexadecimal and binary in this course is because this is what your computer receives when it receives a packet from another computer. Just a string of numbers, or a string of zeros and ones. And this, of course, hexadecimal. So I can look at like this first 4 hexadecimal bytes right here, and we know 4 is simply 0, 1, 0, 0. 5 is simply 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So over whatever network medium is sending this data, it is sending those zeros and ones that get interpreted as hexadecimal. And this is a packet that your computer receives. And we talked about various different forms of inter-process communication, and this is one of those forms, sending network packets through a socket. And we talked about how there were different, this packet, even though it looks like a bunch of zeros and ones, we actually organize it much the way that you organize the PNG file. So we talked about how a PNG file, you have chunks of data. And those chunks of data let you know how much you should read in each chunk, because the first thing you read in a PNG file was the length of that chunk. And the length of that chunk told you, okay, read that many bytes, and that's going to be the entire chunk. Packets, network packets, are organized in the exact same way. That they have chunks, or different layers, as they're called in the HTTP protocol. And each of those layers are organized in a way that's predictable. So we're going to be able to decode this and actually see what are the different layers of this packet. And this is very similar to exactly what you did with the PNG images. So to do that, there is a 7-layer model that we as system developers and system programmers have used for probably the past 40 years. And the way we think about sending network packets across the internet is usually abstracted to the Open Systems Interconnection model, or the OSI model. So you're going to hear about this OSI model all over the internet. And almost everything you hear when you talk about network layer protocols ends up being reduced to OSI model stuff. So there's going to be 7 different layers we're going to talk about. And we're going to go from the lowest layer all the way up to the highest, most abstract layer. After today, we're not going to ever be on the lower levels again. We're going to primarily focus on the higher levels because we want to develop web-based applications. But to understand how this works, we got to go all the way to the lowest levels. So layer 1 on the OSI stack, this is called the physical layer. So the physical layer is the layer that determines how are zeros and ones encoded in the real world. How are zeros and ones actually encoded? So this is things like one physical layer protocol, one protocol that expands into the physical layer is a program you've probably heard about. This protocol called 802.11. So, and if we want to really refer to it, it's actually IEEE 802.11, and it's got a number of different subchapters. So you might hear of like 802.11 N or G or A or AC. There's a ton of different subchapters. And what is this 802.11 thing? Have you heard of this 802.11 thing? No one's heard of 802.11? Something, yeah. Yeah, it's used as something with routers. This is the actual standard that defines Wi-Fi. Yeah, so this is the Wi-Fi standard. 802.11 and all of its subchapters is the physical definition of, or the physical standard of how the Wi-Fi actually transmits radio waves from your cell phone to the router, which, trying to see where the routers are, they usually stick them in the ceilings of these rooms. That looks like an access point right there. So your cell phone is talking to the access point right up there between those lights. And there is a way, using radio waves, which is how 802.11 communicates, that all of your phones are able to send zeros and ones from your phone to that router or access point that then gets wired over physical wires to actually send that data to the internet. So the physical layer, all it cares about is how do I actually represent the zeros and ones as actual data? So, or as actual zeros and ones. So how do I send the radio waves? What should be part of my radio waves? There's also, so if you're using Ethernet, that's IEEE 802.3. That is Ethernet. So if you have like the idea of like a Cat like 5 or a Cat 6 cable, how you actually send data over a Cat 5 or Cat 6 cable is defined in the 802.3 standard. This tells us, oh, you should send 5 volts for 200 microseconds if you want to send a 1. Or you could send 3.3 volts for 100 microseconds if you want to send a 0. It defines how is the zeros and ones actually physically represented in the real world. So that's the lowest level. Once we move on to layer 2, we do not care how the zeros and ones are represented. In layer 2, we just assume layer 1 has taken care of representing zeros and ones. We talk to our EE friends and we say, or compies, and say, hey, how are you going to represent the zeros and ones? Great, can you just give me a packet of zeros and ones? I don't care how you do it. So once we're on layer 2, we don't care what layer 1 does. We just assume it does its job. We've delegated all the hardware stuff to layer 1, to the physical layer. So above the physical layer is layer 2. This is called the data link layer. So this is the second layer as we build up the ability to send network packets through the internet. And the data link layer, this layer is all about how do we send data to the next link in our network. So if you think about the journey the packet takes, the packet's going to go over a number of different links. So if we think about your computer, right, your cell phone, transmitting wireless signals to a router, this is a link. The link is your cell phone to the router. The router is then probably hardwired, or this access point. The access point is probably hardwired to a switch. And that switch, this is another link. So how does that connection, how do I get the data from that box to the next link along my journey to its destination? And then the access point to the switch goes there, and then the switch probably links it to the router. So every single box that's along the way of your journey from your cell phone to whatever server you're connecting to is a link. And the data link layer is entirely responsible for how do I go to the next link and how do I get myself closer and closer to the destination. So all the data link layer is how do I go to the next person in my route to the destination. And as part of the data link layer, we have something called, the biggest thing that you may have heard of in this data link layer is there's something called MAC addresses. So a MAC address is like a hardware identifier that it uniquely identifies your phone from any other physical device that's that's in the current room. Because what the data link layer has to care about is there's probably 40 or 50 of us in this physical room. There's only about 3 access points, or I guess it repeats over there. So there may be about 10 access points in this room. So each of those access points are broadcasting radio waves out into the world. Some of those radio waves are intended for my computer. Some of those radio waves are intended for your computer. Some of them are intended for your phone. Some of them are intended for your phone. So the data link layer says, this packet I'm about to transmit is only intended for your phone or your laptop. So the data link layer makes sure it gets to the right next link in the chain, because there's a lot of other people who are going to receive the packet. So every wireless signal that's sent in this room that's going to any of your phones, it is in range of my phone as well. My phone hears every single packet that everyone in this room is sending. And that's part of the reason that encryption and HTTPS is so important. Because I hear all those packets from my phone, but hopefully I'm not able to make sense of them. Hopefully they're just garbage because we have the right security measures in place. So that's layer 2. We've got the data link layer. So if we say the data link layer is getting from one link along our journey to the next link, then the next layer is going to be the transport layer. So layer 3, we talk about being the transport layer. And the transport layer, or sorry, I'm getting ahead of myself. Sorry, layer 3 is network layer. Sorry, layer 4 is the transport layer. I love the transport layer. Network layer, it exists. We'll talk about it for a sec. Sorry, layer 3 is the network layer. The network layer says it is designed to do host-to-host communication. So the way, remember, every single layer, we're going to abstract things a little bit more. So the first layer, we said this is a physical layer. This is how zeros and ones actually represent. Everything above that layer, we have zeros and ones. The data link layer says, how do I get from one link to the next link? The transport layer says, I have one host. This is my phone. And I have a web server that's somewhere in the cloud that might be illinois.edu. So your phone is a host. Illinois.edu is the other host. So the layer 3 is just concerned with connecting your device, whatever you're on, with a host somewhere in the cloud. It doesn't care how it gets there. It doesn't care about any of those intermediate nodes. We say layer 2 takes care of that. Whoever designed layer 2 protocols will get us from our phone to the other host. We now just care about the fact that we are now connected to another computer. So on the internet, is there an address on the internet that tells us who we are on the internet? Have we heard of anything? Yeah. Yeah, we have an IP address, and that's a layer 3. So IP, or the internet protocol, we have IP addresses. So your IP address is part of your layer 3 information. So every single thing on the internet has a unique IP address, and that is how you address something on the internet. That is like your mailing address for the internet. It's a unique number that tells the world exactly where you live on the internet. And layer 3 is the first part of the packet that we can actually see on a computer. So the data link layer only concerned about getting from one piece of equipment to the next piece of equipment. We will never view the data link layer data usually. But if we look at a packet on the computer, the first part of the packet is going to be the network layer part of the packet. So this right here is the same packet you have on the internet or on your handout. And as part of this packet, I've underlined a few key things. So one of you may have heard of IP being IPv4. So most packets we have on the internet are IPv4 packets right now. And you can see the first digit in our packet is 4. This is saying this is a version 4 packet. And then there's some other digits. So as part of this packet says there's 198 total bytes in this packet. So this is just like your PNG image, where it gives you a length of how much you need to read the entire packet. So here we've got 4 bytes. They're entirely dedicated, or sorry, 2 bytes, 4 hexadecimal digits, entirely dedicated to tell us how big is this packet. We also have the source IP address. So the IP address where I sent this particular packet, so this is the IP address of my office computer probably, is that IP address. And you can see it's encoded in the packet right there. And then I was going to waf.cs.illinois.edu. So if you see so my faculty webpage has this IP address, 18.220.4 or 149.166. And you can see it's encoded in zeros and ones right there. So everything we need the network layer to do is encoded in the network layer of the packet. It basically has a from address and a to address. From my office to waf.cs.illinois.edu as the IP addresses. Yeah? What are the other numbers? Like the other number, oh, these, like the 500 up there. You can look up like IP packet header, and it will show you exactly what all those numbers are. I don't know, I don't have all of them memorized, unfortunately. But yeah, if you Google search like IP packet header, it will describe exactly what every single byte is there for. And because every single byte is sent for every single packet, they're all useful. Like almost all of those bytes have a purpose. They're not just extra wasted space. Cool, any other questions? So remember, layer 1, how are zeros and ones actually physically represented in the real world? Layer 2, how do I go from link to link to link? Layer 3, how do I go from host to host? How do I go from your phone to the Illinois.edu server? Layer 4 is probably my favorite non-application layer, and that is the transport layer. So layer 4 is the transport layer. So that comes after the network layer in the packet. So the top of the packet says, here's the packet, here's how long this packet is, here's its from address, here's its to address. Get it from me to that remote host, do that for the next 198 bytes. Layer 4 says, I don't want to just get to the host. I want to get to the actual program. So this is, we normally call this is port to port communication. And what that means is that every single thing on your computer has a lot of different things talking to the internet. So if we think about a web server, we have like illinois.edu. And there's lots of things that we interact with Illinois.edu. We might send a web request, which in HTTP, so this is a web request, to that computer. But that web request, what app should actually handle that web request? Because if we just give it to a computer, then the OS has to figure out what's going on. We instead want a particular app to handle our web request. We want the web server to see the web request and only the web server to deal with it. So as a bit of trivia, have any of you heard of what port web servers normally run on? Lloyd? Or sorry, not Lloyd. Skander?
Yeah, is it 443?
443 is actually the answer that I wish people would get, because that is the answer, that should be the answer, because 443 is actually the port that HTTPS runs on. So secure web traffic always arrives to your computer on port 443. Matt, you were thinking? Oh, sorry. Port 8080 is actually the development port. And you use 8080 as the development port because by default, port 80 is actually the standard HTTP port. So if you go to illinois.edu without HTTPS, you actually arrive at illinois.edu. You actually send a packet to Illinois on port 80. That's a destination port. So if you're doing development work, you often are working on like port 4000, 3000, or port 8080, some high port, because the lowest 1024 ports are reserved for only kind of privileged processes. So if you're doing development work, you always use a port that's above 1024. But yeah, we have every single port on our computer. We've got the ability to have port numbers from 0 to 65,535. So we've got 64K ports available to use. And we define a few ports as ports that we expect things to be on. So port 80 is where we expect the web server to be on, or 443 if it's a secure web server. If you're connecting to a computer via SSH, well, we expect SSH to live on port 22. So, or we can say, I actually want to connect to a particular port and give that port number. So by doing port-to-port transit, it's saying, the network layer gets you to a particular computer. The transport layer gets you to a particular program on that computer. It connects you to a particular app. So it tells what port number on that computer are you connecting to. And that port number is going to be assigned to one particular app on the operating system. So if we look at a transport layer protocol, this is everything we expect to see. So the first thing we see in the transport layer, this is a TCP packet, is going to be BAFA. So when I was connecting to my own web server, connecting to waf.cs.illinois.edu, my computer said my outbound ports, the port that's leaving my computer, is going to be some random high port. So the thing that's expecting the data back, I'm sending a packet and saying from port 47,000 and some, I'm sending that information on that port out into the universe. And because I'm connecting to waf.cs, I'm connecting from 47,866 to my web server, which is waiting for me on port 80. So these bytes say, hey, operating system, when you get this packet, when that host gets this packet, it needs to get this data delivered to whoever's living on port 80. And we know that from the header from the fourth layer, from the network layer data. Then there's a bunch of other data. So there's like a checksum here. There's a timestamp of when this packet was actually sent. So we've got checksum data, we've got timestamp data. There's a bunch of other fields there's a bunch of options you can use on the network layer, on the transit layer. So there's a bunch of stuff in this packet. But the key idea is that the transport layer goes from one app, so like your Chrome web browser that's making the request to the web server, and goes to the web server app that's running on whatever computer is running waf.cs. So basically, what we've done is we said, all of these are zeros and ones. There's somebody who decided the physical layer protocol. How are those zeros and ones represented? Then there's someone who decided, how do we go from link to link to get us closer to the destination? Once we know how to get to the destination, how do we have two hosts communicate? How do we identify where they are on the internet? And now we have two apps communicating. We have your web browser communicating with my web server. So we've kept building it up, and we've kept building it up. And this is how a packet actually gets delivered. And then we reach the top three layers. And they used to try and separate layer 5, 6, and 7 into 3 different layers. Because they actually have names. If you look them up, I think they are like the security, the session, and the application layer. In modern times, we've condensed all 3 of them, and we just call them the application layer. We don't divide up the tasks of the rest of the packet contents into other layers. There were attempts previously to say, oh, we're just going to put security on layer 5 so that everything above that is secure. But that ended up not working out so well. So the first 4 layers, the design idea years and years ago, still stays true. But in today's world, layers 5 and 6 and 7 are just the application layer. And this is everything else left in that packet. So all of the other data. So we saw at the network layer, it said there was 189 bytes in this packet. We saw the network layer had some of those bytes. The transport layer had some of those bytes. And now the application layer has the rest of those bytes. And this is the only data that your program is going to actually receive. So as a programmer, you're just going to see these bytes. Because the network layer and the transport layer just gets that data to you. You have to carry those bytes along the internet. But once they get to your program, all you see is the application layer. That's all your app's going to care about, despite the fact a bunch is going on to get you that data. And this particular packet is an HTTP packet, which we'll talk about later. But you can actually decode this. This is all just ASCII data. So this is just, and I literally, like all of those characters are exact ASCII characters. You can look up an ASCII table, and you can convert all of those bytes into their ASCII equivalent. Nothing fancier than ASCII. So if you look up what hex 47 is, that is going to be capital letter G. So any questions on the different layers, on how we can look at a packet and identify the fact there's lots of different layers that happen and the purpose of each of the kind of 5 layers in our OSI model? Yeah, Jake.
So the application layer is always just like an ASCII conversion of all this stuff is just ASCII characters converted into hexadecimal?
Ooh, great question. Is the application layer always just ASCII characters? The answer is no. It's going to be up to whatever app we write. So this happens to be one example. This is HTTP. There's other protocols like SSH is encrypted, so it'll look like garbage, basically. Yeah, so the application layer, it's up to the app itself. So you could design your own protocol. Like if you're sending data in a certain way, you could design your protocol. Yeah, it's completely open-ended. It's whatever you want. So just kind of summarize everything. If we think about the, and we'll talk about the specifics of this in the later part. If we think about a full packet journey, we can think about how there's a packet that originated on your cell phone. And on your cell phone, this packet before it leaves your cell phone, as it's about to go over the airways, it's going to have an 802.11 header. So we said 802.11 is the Wi-Fi data, right? That's how we transmit radio waves of the data on your cell phone that needs to go to the internet. It then has a IP header. This is our layer 3. And then it has a layer 4 header. So if it's making a web request, it's got a TCP header. And then it has an app data. So this is our HTTP request. So those 4 things are going to be present when that packet leaves your cell phone. You have data link layer stuff, you have IP layer stuff, you have TCP layer stuff, and you have HTTP stuff. And then as it travels over the network, it's going to have its 802.11 layer replaced with a new 802.3 layer because it has to make it to the next link. but we copy over all of the rest of the packet. So as you move through the internet, you're going to basically be changing your data link layer every single step of the way to get you one step closer to the actual end server. And in general, you're not going to change out your IP layer or your TCP layer until you reach the remote host. So the only thing that usually changes on the internet is you're going to change out your data link layer to different types of data links as you move along. And eventually, once you get to the end host, the host is hopefully if everything goes well, your host gets a full packet that has IP data, TCP data, and app data. Then it delivers the app data to the particular program that's associated with handling that request. And this is the base rules that we go by on the internet. So there's a lot of things that we're going to talk about in the second half of this course that begin to break certain things I say here. Like there are things called load balancers. So when you visit google.com, there are millions of people also visiting google.com at the same moment you are. So there can't just be one server that handles google.com. So instead, there's things like load balancers, where google.com actually, there's a computer that basically takes that packet and says, okay, actually I'm going to rewrite the TCP or the IP headers to direct it to a server that actually handles your particular request. So we can think about how do we build on top of this to scale, and how do we expand upon this. But if we just have one server and one client, this is exactly the model it takes. So I want to just mention two specifics on the protocols that you will interact with and you will see on your journey if you end up doing some systems level work. So the first thing are layer 3 protocols. So these are your network layer protocols. There are basically only two of them. And as we mentioned, they provide host-to-host communication. So it is the address of your computer. So the address is your IP address. And there are two IP addresses that exist in the world. There's IPv4, which is what you look at. These are 32-bit addresses. And so they are read at like 128.171.33.180 or whatever. So they have, it's written as 4 sets of 8-bit numbers. And they're separated by a period. So you probably have come across some of these. Like you've probably seen these numbers that exist. But if you only have 32 bits, that means we only have 32 zeros and ones. That means we only have 2 to the 32 possible numbers. So 2 to the 32 possible IP addresses, going from 0000 all the way up to 111111. We only have 2 to the 32 of them. 2 to the 32, well, if we do the math, that's only 4 billion combinations. But how many people are on the planet? 7 or 8 billion, right? So do we have a problem? Because, I mean, how many IP addresses are we each using right now? Like, our phone's got an IP address, right? Some of you may have an internet-connected tablet. Like, right now, I've got a phone up there. I've got this laptop. I've got my stylus. I've got this machine up here, too. Like, I've got 3 IP addresses just hanging out right here. Not to mention, like, another computer in my office, computer at my house. My wife has a computer that she's on right now, I'm sure. So just my universe is like probably 10 or 20 IP addresses. My smart thermostat probably has an IP address. So if there's 78 billion people in the world, and there's only 4 billion IP addresses, we're running out. As more and more people get connected to the internet, there's not enough IP addresses. And there's been hacks that have been done. Like you end up getting your local network IP address. So like my smart thermostat actually isn't on the internet, it's just on my local network. So it shares an IP address with other devices. But we're running out of IP addresses. We don't have enough of them. And it's becoming a real big problem. So IP4 addresses, I think in 10 years are going to be gone. You're never going to see IPs that look like this. But what happened about 10 years ago is they wrote a new protocol called IPv6. So IPv6 are 128-bit addresses. And they are written as 8 sets of 4 hex digits, separated by a colon. So if you see an IPv4 address, it might be like AC82 colon 4CDA colon AC82 colon so forth, so forth, so forth. There's a special way, so a lot of IPv4 addresses, or IPv6 addresses, because there's so many of them, sometimes we say, there's a whole bunch of zeros in them. So there's a shorthand, what you'll actually usually see is an IP address that looks more like this. This double colon means that there are 0, 0, 0, zeros in between. So in reality, this is commonly what you see for an IPv6 address. Is you see something that's a little bit shorter because there's a whole bunch of zeros in the middle, because we don't need all 128 bits. We're running out of 32-bit IP addresses, but if we just add a 33-bit, we've doubled the number of IP addresses. So 128 bits is like super future-proofing ourselves. And we've got this convenient way to write this IP address. So I want to talk about one last thing on IP addresses. And that is, in an IPv4 address, we have one very, very special address that will become our best friend. So actually not on the back side, so back still here. On the IPv4 address, there's an address 127.0.0.1. That IP address has a name, and that IP address is localhost. So every single computer, by specification, refers to itself at the address 127.0.0.1, which has also got the name localhost. So as you do local web development, you're going to probably connect to your own server on your own computer. You're going to do that as part of MP6 and 7 and 8 and 9 in this class. That computer, that number is 127.0.0.1 or localhost. Both of them refer to the same thing. Localhost just translates to 127.0.0.1. This is the address of your own computer, no matter what computer you're on. You don't leave your computer when you connect to 127.0.0.1. You don't actually go out to internet anywhere. It is just a way to get a socket to yourself. So it's a great way to test web applications by running it on localhost. So you're going to see this come up a bunch. In IPv6, it is : 1. So that is all zeros except for a 1. So that is also, and that is the local host for an IPv6. So it's actually kind of a cleaner address. So localhost is, so If your computer is set up to use IPv6, which I think some of the newest Macs have started converting over to IPv6, you may see that you connect to your development server by going to ::1. Some Macs still use the 127.0.0.1, our local host. So these are ways you can connect to your own computer without needing to go to the internet. So that's all we really are going to talk about with IP addresses. They're numbers that get us to a destination computer. We need to know what the destination computer is. We'll talk about how there's kind of clever technologies to actually help us get from our local computer or from a name to an IP address. So if you go to google.com, you first have to look up what is google.com's IP address. But that's a whole different story that we'll cover later. We just know that if we know the IP address, the IP protocol gets us to that destination. Any question? Yeah.
What's the difference between a socket and a port?
So a socket is, so the difference between a socket and a port, a socket is a thing that you actually send data over. It's like a pipe. When we talk about a socket has to be, a socket is going to be bound to a particular port. So the socket is the mechanism that we receive data through. So the socket is what we send or receive data from as a programmer. And it is, a socket lives connected to a particular port. It's like the abstraction that actually gets us the data. So we're gonna build a socket when we want to receive data on a port. So you'll build socket, you'll actually write your own socket code as part of MP5. So you'll build your own simple web server. Yeah.
I'm like thinking of an analogy for that. Would this be a dumb analogy or maybe it's more? So the socket would be like the mailman kind of like a bunch of mailboxes bringing the data to the mailboxes, and then each mailbox is like a port.
Yeah, basically, if each app is like a, if each app is a mailbox, the socket would kind of be the mailbox, I would say. I don't know. Because socket's the mechanism that you actually get the data. So it's hard to kind of figure out like what exact thing, because the socket really is everything that involves with delivering the data to your actual application. So it's receiving the data, transmitting the data. It's what does the read and the reading and the writing. So it actually writes the letters. You send it the data, it actually writes the data down. Yeah.
Is it possible for IP standards to be like deprecated? Like as in there are certain like networks that won't accept like IPv4 requests, or
Yeah, is it possible for IP standards to be deprecated? Sure, definitely. But I can tell you, if you start a company that doesn't accept IPv4 requests, you're not going to get very many people at your business, because so many people are still using IPv4. So what modern routers do is they accept both v4 and v6. But yeah, one day, eventually, we're going to have to just say, okay, we're going to turn off v4. But that's going to take a really, really long time. Yeah.
actually, is there like a V5 or a V3 or anything?
That's a good question. Why is it v4 and v6? I have no idea. They're the only two that exist on the internet broadly. Is there a v5 that somebody wrote? Possibly, probably. They probably wrote v5 and probably there's a committee and lots of people looked at it and they probably found problems with it. And they sort of evolved to v6. I don't actually know the history. That's a great question though. Yeah. Is it possible that OSI becomes deprecated? I mean, certainly sure. I mean, we're already seeing OSI, it's more like a framework than anything. So I feel like we've already seen that like layers 5, 6, and 7 have kind of been smashed together. If you read the original OSI standard, it still has a layer 5, a layer 6, a layer 7. I mean, these are living documents, kind of. So people don't really talk about the security layer anymore, even though that's layer 5. So I feel like as systems, we sort of see what exists, and we're like, oh, we want to build on what exists. But sometimes it just doesn't work for us anymore, so we change it a little bit. And eventually, if enough people change it, they may decide to publish OSI version 2 standard or something. So standards evolve. We talk about HTTP. the HTTP version 3 is coming out soon. So the standard that we use to communicate web page development, that's changing, that's evolving. So that's the beauty about standards. The systems is all about you and a bunch of other people agree on how you're going to communicate. You share that with the world, and if everyone agrees that's how we're going to communicate, now we can actually communicate. So that's really what systems is all about. So we've talked about layer 3. We've talked about how to do the network layer. But there's also 2 layer 4 protocols. So I want to talk about 2 of these layer 4 protocols. So layer 4 protocols, these are endpoint to endpoint or port to port communication. So this is getting from my Chrome on my cell phone to your web server. And not the actual just host, but to the actual Apache or Nginx web server that you're actually running. And there's basically 2 ways to communicate data from one app to another app. One way is called TCP, the other way is called UDP. Pretty much these are the only 2 protocols that will exist on the internet for now. If you try and send something without a TCP header or UDP header, it's going to reach somewhere in the middle of the internet. It's going to be like, I don't know how to deliver this. So every packet sent on the internet is generally going to be TCP or UDP. And there's a number of different features that these provide for us. Because the network layer, it provides endpoint-to-endpoint communication. And the network layer, depending on whether or not we choose UDP or TCP, we get different guarantees. So one thing we might want to talk about is we might want to have a feature where the communication is connection-oriented. So do we want to establish a connection with who we're talking with, or do we want to just send them a packet and hope they receive it? Do we want to have a conversation with them, or do we just want to blast data at them? So TCP is always connection-oriented. So when you connect to a web server, you're having a conversation with that web server. UDP is not. So UDP just blasts data at you, essentially. It's not connection-oriented. It's just data-oriented. It just sends data to a particular address. So the second thing is we might want to know, we might care about whether or not we have an in-order data, so whether or not we have a data sequence. So that means if I send ABC from one computer, do I get ABC at the other computer? Or do I possibly get BCA? Because as things travel across the internet, one packet may take longer to get to the internet because some computer along the way is slower. So do I want to make sure if I send the letters ABC that you get ABC, or are you okay receiving BCA out of order transmission? If we're using TCP, we get this. If we're using UDP, we don't. So UDP doesn't guarantee that the data we sent arrives in the same order we sent it. It will like 99.9% of the time. It almost always gets there even with UDP in the same order. But there's no guarantee that it's actually going to get there in the same order. Third thing is, do we have guaranteed delivery? So if I send ABC, do I know I'm going to get ABC? Or what if I only get AC? What if B gets dropped along the way? Is that something we're okay with? Can we handle if a few bytes don't make it? If our app can handle a few bytes that don't make it, we can use UDP, because TCP, it guarantees delivery. TCP has guaranteed delivery. UDP does not. So there's for all of these nice features, for this connection-oriented approach, for this idea that we're having a conversation with another client, for the idea that we get ordered, reliable, guaranteed delivery, we have to pay a cost for that. The overhead for a TCP packet is large. It is about 5 times larger than a UDP packet. So every time we send a message with a TCP connection, we're spending about 5 times as much overhead to do that versus UDP. So the UDP overhead is small. So we're basically spending extra data to ensure that we have reliable delivery and in-order delivery. We have one of those things in those numbers in that message of the TCP header. One of that's the sequence number that says what sequence is this message. So it's going to make sure that it only delivers message 1 after it's received message 0. And if it doesn't, if it receives 0 and 2 and doesn't receive 1, it's going to ask for 1 to be retransmitted. So TCP has a bunch of features that gives us reliable in-order delivery at the cost of a lot more overhead. So what is its applications? So we know from here that HTTP and HTTPS, websites, web traffic is TCP. I don't want my web page to have my paragraph 2 come first. I need to make sure whatever I send as a web server gets to you exactly as I intended. What are applications that we might use UDP? Why do we care about UDP? Where might we want smaller overhead? So what? Maybe FaceTime. Yeah. So video. Audio. So any real-time communication is going to prefer to be over UDP. Because there's lower overhead, UDP is actually faster. So video communication is one that you sometimes see like artifacts inside a video. Like I'm sure you've seen like video get grainy for a little bit, or someone like jump around in a video call, especially when there's poor quality. That's artifacts of UDP. The fact that you may actually get packets out of order. Sometimes you hear like, an artifact you sometimes hear on like video calls is if somebody has a bad connection, you sometimes get all of their audio at like 1 split second. So they sound like they're talking like 4x speed. Have some of you seen this? Yeah, you've seen this. This is all of that data getting delivered all at once because there was some connection issue somewhere along the internet. So their data was all getting delivered at like basically the same time after they spoke. This is something that UDP is causing. So when connections go bad, UDP has problems because it's designed to just get a data there as fast as possible. Doesn't care about the order, doesn't care if you're missing packets. It just tries to get the data there as fast as possible. TCP, on the other hand, cares about accuracy over speed. So you as an app designer, you're going to just have to decide, do I need accuracy or do I need speed? And that's a trade-off that we get to make. So you can choose, do you want TCP or do you want UDP? Most of the time, you're probably going to choose TCP. Because TCP accuracy, when you don't guarantee that your packets are in order, things get really, really, really complicated. Like it gets hard when your packets may not be delivered in order and may be missing data in between. That's hard to think about. That's hard to program. But video encoding, audio encoding, all of that stuff, that's all done with UDP. So that is how network packets and sockets actually exist as we travel over the internet. And all of that is done so that we can finally be at the application layer. And we want to care about how do we build web services? How do we run HTTP? And this ultimately begins the end of our journey on the first act of this class. Because in the second act of this course, for the rest of the semester, we're going to live on top of HTTP. We spent the first 7 weeks just building up to this point, that we can say, we're going to talk about this protocol so that we can start using this protocol to help us build web-based and cloud-based applications. So one of the main ways that we build applications in general is this idea of building web services. These are applications that communicate using the HTTP protocol. So we're going to be building on top of the HTTP protocol for the entirety of our Python programming. Everything we do in Python is going to be building on top of HTTP. And HTTP packets come in two types. So, before I even talk about this, HTTP protocol, this is a TCP IP protocol. So some people, you'll hear sometimes it's called TCP IP. This says that HTTP, it's running TCP. So TCP means that we have guaranteed delivery. We have in-order delivery. The packet that we send is the packet we're going to receive. So it is running on top of TCP. All those guarantees and all that overhead we talked about, that's included in HTTP. So it's already made the choice of what our layer 3 and layer 4 decisions are. We don't get to choose this. Once we're in HTTP, HTTP is our application layer. It is our level 5, 6, and 7 protocol. And an HTTP packet comes in two forms. It comes as a request, is the first type of packet that we're going to look at. So as a web browser, your web browser is going to make a request to a web server. Or your program that needs to call a web API is going to make a request in the form of a request packet. And that request packet is going to have a very, very well-defined format. And it's part of HTTP spec. You're going to get a look at the HTTP spec as part of MP5. But the spec is actually pretty straightforward. There's 4 things to note about it. So the first thing to note is the HTTP specification. It delimits the lines by /r/n. So the first thing is the line delimitation is /r/n. So if we go way, way, way back to this packet, you can see that 0D, 0A is the line delimitation. And you can see every time we have a new line in this packet, we can find 0D, 0A, which is a /r/n character in the actual packet itself. So if we look at the zeros and ones, every one of these /r/n's is going to appear in the 0 and 1s. This tells us how each line is organized inside of a HTTP packet. So it's always going to have a /r/n at the end of every single line inside the packet header. And the first line is special. So the second thing to notice is line 1 has the HTTP action, location, and version, separated by space. So notice that we are making a post request to extract using HTTP 1.1. So line 1 tells us what type of request we're making, what is the location of the request that we want from the web server, and what is the protocol version. Then every other line is going to be the headers. So headers are key value pairs separated by a colon space. So we can send any number of key value pairs along with our request. So here I have host is localhost 5000. So this was me actually running a little sample application. This is actually me working on MP6. So this is actually a request you're going to send as part of MP6. So you're going to send post request to actually extract a hidden GIF from some images. So you're actually going to get a callback to MP2, but in Python. So headers are key value pairs, and they end when you see an empty line. Empty line ends the headers. So you can think about this as an empty line, but if you actually think about what the characters are, because I've broke them up into lines, right? So we've got all of these lines here. The way I actually usually think about it is detecting the end of a header. I usually look for 06OA, 06OA, or sorry, ODOA, ODOA, again and again and again, for the 2 times in a row. So we basically, if you look at this not broken up by lines, it's basically /r/n/r/n, right? It's those 4 control characters in a row. It looks like a blank line as soon as you break it up into lines, but at a byte level, it's just ODOA, ODOA. So, and then everything after the headers is the payload. The payload's going to be defined by the content length. There's one special header that tells us how much payload there is, and the payload is always going to appear after the end of the headers. Yeah?
Is there a reason why the page return happens before the new line?
No idea. It's the standard. Back in like the 1970s when HTTP was first being invented, that's what they decided to do, and we're stuck with it. Yeah, that's the joy of systems. Like, could have they actually just put like /n there? Probably. Do we need /r/n? Who knows? But that's the way HTTP has been done. So every request you see everywhere is going to always follow this because that's what the standard says. So that makes up the request header. So this is going to make a request to a web page. That web page is going to, or a web server, that web server is going to return the resource that is located based on the request that you made, based on the action you make, like a get, a post, or whatever that verb is, and then at a particular location. So this is looking for something at extract. And then, once a web server or a web service has received that request, it is going to send back a response. And the response looks incredibly similar to a request header. It still uses /r/n as the line termination. Same idea here. It still has key value pairs after the first line. The first line, though, is now going to be the status line. Now has 3 separate things on it instead. So the status line now says, what version of HTTP am I responding back in? So I send you an HTTP 1.1 packet. This server says, I don't speak 1.1, so I'm going to downgrade us to 1.0. It's okay. It works. And then it's going to respond with a status code. This says 200. And the HTTP standard defines what these different status codes means. And then it gives us an English language description of what the status code is. So 200 says, okay, I've processed your request, everything looks good, here's the data you requested. You'll see that we have the content length header again. This key is a special key. That key tells us how much data there's going to be after our headers. So after that /r/n/r/n, we have all that data at the end of the packet. And this allows us to send a response in a way that is understood. The only key difference between the request and the response is that first status line. So if you look at that status line, you'll know exactly what kind of response it is. And the status lines have a number of HTTP response codes. So you've probably heard of code like 404, right? 404 is classically file not found. Yeah. So 404, file not found. So that's probably the most famous response code, but HTTP actually defines response codes for the entire spectrum. In fact, the 1XX response codes are known as informational response codes. So like one thing, your web service may say, continue. So you may build a service that needs multiple packets of data. So someone may send you may build a web service where someone sends you some initial data, and it says, okay, yep, this looks good, keep continuing, keep sending me data. So I might send a 100 packet. There's 2XX codes. All the 200 codes are success codes. So 200 is okay. 201, like if you're building a web service, you might want to create an entry into a database for them based on some web service request you made. So 201 is actually a response code to say, I created something. So as you build web services, you may respond with a 201 code saying, yeah, you sent me a request to actually create something, I created it. 300 response codes, those are redirects. So redirects may say this page is moved, this page is now somewhere else. A different redirect, the 300 code that's actually seen the most is actually 304, which is not modified. So one thing you're going to see in the headers that you started to work on is you're going to see all these cache control things. So cache control and e-tags. This says, this is an identifier to say that the content is this hash, and if the content hasn't changed, I don't need to send it to you again. So if you want to cache an image, this is what this server is basically saying that you can cache this for up to 43,000 seconds, and it has this identifier. So I could ask the server, has this content changed? Do I need to download this image again? So those are 300. 300s are redirects. 400s are client errors. So these are errors made by the person making the request. So if they made a request for a file that wasn't on the server, that's their fault. The server did everything it did perfectly. It was able to complete the lookup for that file. The client goofed up. It made a request that wasn't found. 5XX error codes are server errors. So if we, as web developers, as app developers or web service developers, if our programs goofed up, if we ended up with an exception, if our code threw an exception and can't continue processing it, we're probably going to return some sort of 500 level error that says, oops, our code threw an exception. We should probably debug something. So 500 errors are server errors. And you'll see like 500 is an internal server error. It's kind of the generic error. Error 400 is, for example, a bad request. So if you malform your HTTP request, the server might say, you sent me garbage, I don't even know what you're talking about, try again. That was a bad request. So these are the status codes that we have in HTTP, and there's a ton of them. So these are just the ones that are common. If I were to say, hey, HTTP status codes, there are going to be literally hundreds list of HTTP status codes. You're going to see that any one of these numbers have a whole bunch of different individual codes that we will use a few of them as we need to as we build apps. So as we communicate data and as we build web servers, we're going to get familiar with a few of these because we're going to use the HTTP standard as our way of communicating data. And this is what a web service does. It builds on web technologies to provide a service that may be a web page, but more often than not, it's going to be doing far more than just displaying a web page. We're going to be like processing images, transforming data into audio, and doing a whole bunch of other stuff on top of web services. Yeah?
Are these status codes generated by a computer, or do we have to determine which ones get sent out?
No, we're going to be, when we send a response back in our Python MPs, we decide what status code we want to use. So they're set. Like, we can't just make up our own. We can't say status code 418. If we said status code 418, let's see, is 418 defined? I'm a teapot. Apparently there's a story. It's an April Fool's joke. Okay. So 418 is a crazy status code. So basically, all of these status codes exist. We can't change what they are. Those are based in the standard. But we're going to use these status codes so we can build an app that communicates with the rest of the world. Because the people who are going to be using our stuff, we're building stuff for millions of people. We can't just make our own thing when millions of people are using our web app. We've got to rely on standards so that when people consume our app, when people consume our API, that our API works as expected. So I wanted to spend the last 2 minutes we have together briefly talking. So next week is midterm 1. My goal is to make the midterm 1 as stress-free as possible. Like, I don't want the midterm 1 experience to be a stressful experience. I just want to make sure you know the system stuff that we're learning. So the practice exam that I've already put up is identical in generation to the real exam, with the only exception being the coding problem is different in the real exam. So I have a practice coding problem already part of the exam, so you can see the interface, you can get used to the autograder, all that kind of stuff. That question is going to be different. All the multiple choice questions just literally come from randomly selecting among all of the possible homework problems. You can generate an infinite number of practice exams. So for the non-coding question, there's no reason you shouldn't ace the exam. You will be able to generate as many practice exams as you want. You just have to go into the CBTF and show me that you actually know this stuff without Googling it. So you have the full set of questions that you might have on the exam through the practice exams. Then you'll have one coding question to do in the CBTF next week. Because we have an exam and we're taking it outside of class, you get that time back. So there's going to be no lecture next Thursday. So a week from today, there's no lecture. On Tuesday, we're going to talk about kind of finishing up Act 1. We're going to bring this all together. We're going to have our last conversation that involves C code ever this semester. And after that Thursday, we're going to be entirely in a Python universe. So basically, we're going to wrap up Act 1 of the course. We're going to finish the system stuff. We went all the way from zeros and ones, how a CPU works, how memory works, how operating systems work, how devices actually happen, how we get data onto a computer, how data gets loaded into the CPU, all the way up to networks. And now we see how a network packet actually gets sent. So in MP5, which is your very last CMP, you're going to build a server that you're actually going to connect to with Chrome. So you're going to test it. We have test cases, but your final test case is open up your web browser, connect to your own web server, and have your C program actually understand the request that Chrome or whatever web browser you're making is making to it. So you're going to do this in C, and then you're going to see in MP6 how Python does all of that for you in just one line of code. And you're going to hate me for having you do it in C. But you'll understand how that one line of Python code actually does 300 lines of C code. And you'll actually see at a systems level how this actually works. So we'll come back here on Tuesday to actually finish up Act 1, talk about how the last bit is C, and then you've got Thursday off. Make sure to sign up for your midterm time if you haven't signed up for it already. Midterms next week, practice exams already there. Midterm is hopefully as stress-free as possible. I'll be here if you have any questions. Otherwise, have a fantastic weekend. Good luck in the midterm, and MP5 will be out tonight.